I would like to introduce the moderator for the next session, which I think is going to be a very interesting and exciting session. And I promise not to steal the thunder. So the only thing I can do is introduce our next moderator, Sin Sikora, Industry Outreach and Technical Activities Director of the IEEE Communication Society.
Thank you so much. Thank you. All right. Hello, everyone. Welcome to the Research Collaboration Pitch Session. This is the first of its kind. It's new for ComSoc. And first of all, I would like to thank the conference organizers for including the pitch session in the program today, because this is a new and innovative approach to bridging the communities of academia with industry. And so they are taking a bit of a chance on us, but this should be the first of many pitch sessions. We've already got another one of these sessions planned for GlobeCom in a month in Taipei. I do want to make sure that you know that the core mission of IEEE Communication Society ComSoc has always been to advance communications and networking technology for the betterment of humanity. However, this progress cannot be achieved in a vacuum. It is the result of collaboration between the brightest minds in academia and the innovative leaders in industry. And this is why when we got together a group of industry leaders in our industry advisory group in June, what they expressed to us, their biggest need as industry partners for IEEE ComSoc was to have better opportunity to connect with academia. That's why we started the ComSoc Research Collaboration Pitch Session. It's a unique opportunity for the top academic minds to present the bold problem spaces that they're tackling to innovation scouts from our industry partners, with the goal of starting conversations, hopefully getting collaborations in place with those industry partners. So I would like to just point out that if any of you are interested in participating in future pitch sessions, there are calls for proposal that you will be able to submit your research for, and you too can be up here giving a 5-minute high-impact pitch to a group of innovation scouts with the possibility of collaborating with them. We also will be putting this on YouTube, making sure that there's a lot of exposure. So even if there isn't a match between these research opportunities and the innovation scouts that are here today, there could be a match with other industry partners that we work with. So I just want to first introduce to you our innovation scouts. These are the people who are going to be on the stage listening intently to the wonderful selected research pitches that we have lined up, and they'll be asking the probing questions. So the first person I'm going to introduce is Pavel Dutta. He's the Senior Manager of Open Innovation and Strategy from Samsung. Pavel, please. Thank you. Okay, the next person I'd like to introduce is Richie Leo, the Master Researcher from ZTE. Richie, yay! A little more enthusiasm. Okay, very good. All right, the next innovation scout that we're going to introduce is Reinaldo Valenzuela, the Director of Communications Theory at Nokia Bell Labs. Woo! And the next Innovation Scout is Hao Xu, from the VP of Engineering and the head of Qualcomm Research China. From Qualcomm, Hao, welcome. And the last of our Innovation Scouts joining us today is Junping Zhang, the principal engineer of Huawei Wireless Technology Laboratory from Huawei. Thank you. And I would like to thank all of you for joining us today. I appreciate your time. And we're hoping that this sparks some interesting conversations and collaborations.
All right, so I'm Sharif Azmi, and I'll be talking to you about extreme edge computing. This clicker work? Right. Over the last decade, we've been exploring the computing continuum. We started with the cloud at the heart of the network, and we kept pushing computation towards the end of the network as close as possible to the end user. Both academia and industry worked hand in hand to trailblaze this exploration, making applications today that were once unimaginable available to everyone. Today, we're providing services that were once unimaginable. But at some point, there is a wall that we kept hitting as we kept trailblazing. This wall lies at the very extreme edge of the network. This is missing out on a lot of potential. This potential lies in the idle resources present on millions, if not billions, of devices. Now, the last mile, the extreme edge, is really a beachfront property. In such a beachfront property, you're right next to the end user. The end user is surrounded by a crowd of devices, and these devices are connected and powerful mini computers that are just right next to the end user, sitting at the very extreme edge of the network, closer than any edge server will ever be. But they're sitting there idly. They're doing nothing. Now, this is frustrating. Can't we do anything about this and mesh them together somehow so we can actually end up making them more useful? The problem is it's not really that simple. The devices over there are everyday devices on the extreme edge. They are resource-limited devices. They're resource-constrained. And they have a job that they're expected to do. They're multi-tenant devices. On top of that, they're laden with a lot of uncertainty. This gives us a troublesome mix. If we were to tap into the bounty of the extreme edge, then we have to deal with that troublesome mix somehow. This means we need to develop distributed, stochastic, and ad hoc approaches in real time to handle and harness all of these resources. Now, a few years ago, it was just economically infeasible. It would be crazy to try to attempt to harness all of these resources. But today, we believe is different. We're reaching a point where we have a convergence between communication technology and computation technology. There are things such as software-defined radio and virtualization that are actually making this possible. We believe that creating a computing fabric on the extreme edge is no longer a dream, and eventually it will become a reality. And we want to be a part of the reality. But one might ask, why should we bother with the extreme edge in the first place? The reason is because we have to. The extreme edge we have to tap into it because computing has become very expensive. If you were to look at the computing market, the chip market, you will realize that there is a bottleneck over there. The computing supply is being outpaced by the demand for AI as well as cryptocurrency. This has led the prices to hike in a way that is harming, that is creating barriers to entry and hindering innovation down the supply chain. And unfortunately, this is not going to go away any soon. So we simply need an alternative for that, okay? So what are we doing at the Queen's TRL? We are orchestrating this mess. So we developed techniques for slicing a workload and distributing it over this extreme edge devices. We can find communities, we can benchmark them and measure their performance, as well as we have developed prototypes and test beds for that. So where are we right now? Right now, if we were to look at extreme edge computing, you can think of it as a circle. The left half of the circle represents a user-flavored extreme edge. You can think of that as a crowd-powered system like Uber for computation. And on the right side, we have an enterprise-flavored edge. This is a more reliable, controllable one, but it acts in a dynamic environment that has a lot of uncertainty. If we're to look at the technology readiness level as a metric over here, we can see that we've progressed a little bit over the last 4 years to TRL 3 and 4. We're somewhere between that, and that was part of an NSERC Alliance project that has $3 million. We recently finished that project. On the enterprise part, we're kind of working with the National Defense of Canada to explore powering semantic communication on the tactical edge. Who are we? We're the Queen's TRL Laboratory, 25 years legacy of experience with under the supervision of Dr. Hossam Hassanain. We collaborated with industry leaders such as Bell and Ericsson, as well as government agencies. I'm Sharif Azmi, and our team includes my friends and partners, Sari Ar-Raham and Rawan Al-Khatib. Thank you so much for listening. And yes, this is a QR code for our website.
Okay, that was wonderful. Thank you very much. First research pitcher of all research pitches. So Innovation Scouts, can I please open it up for questions?
Okay, so it's a little bit rough, but we hear often there is no free lunch. And the idea of relying on the opportunistic idle compute cycles is being around. The difficulty is what is in it for the device owner. It's not for free. You're going to drain my batteries. You're going to perhaps interfere with my traffic capabilities. Could create perhaps bottlenecks. I don't know. Why would I allow it? Why would I even bother and not even actively seek a VPN or firewall to stop you from doing it?
All right, so the core of my PhD is actually about paying incentives to crowd power the system. So we want to lure the users in by giving them incentives. And right now, phones have become a hassle because many people are getting addicted to it. And some people are actually, there is a market for productivity apps that people are signing up for and paying subscriptions. And that's a waste of money, in my opinion. I think it would be best if we tell them, I'm going to pay you money if you leave your phone. Yeah.
Yeah, very nice presentation. Can you summarize in 1 or 2 sentences, what is the major technical breakthrough here that's different from current edge solutions? And how does it tie into wireless communications? Oh, this is mostly about processing.
So a big problem is uncertainty, and that uncertainty stems from 2 things. The devices are different, and the users themselves, the way they act is also different. And this is at the very extreme edge of the network. So we kind of need to think of many dimensions. How are we going to control this? How are we going to predict this? How are we going to plan and proactively prepare resources to provide a service based on that? So I'm thinking I have not answered your question here, but maybe we can kind of dive into that later. Would that be okay?
Let the other people ask questions first. If we have time, I can follow up. Yeah. I'll let the other people ask questions first, then I can ask further questions.
Thank you so much.
And thanks for the presentation. So I got 2 questions, but the first one is, so you describe an edge computing scenario, right? But there's the other options of doing the computation, for example, in a central server. So can you...
Sorry, sorry for interrupting you, but I can't hear you properly. So
Okay.
can you...
So the scenario that...
I'll come to you. It's much easier. Yeah.
Okay. So the...
Thanks.
So the scenario that you described is edge computing, right? But there's other options like doing the computation as central server. So can you use a specific example to illustrate the advantages, for example, a particular use case that would benefit from the edge computing instead of doing the computation at the servers, central server?
That's a tough question. So one examples we've thought of, and this is part of the work we're doing on the tactical extreme edge, is when we have, like whenever we enter like a jammed and a denied zone where we don't have any central computational access to any central computational resources. So what do? I have to harvest it from whatever is nearby me. So this is one application. So if we suppose that there is an image that I need to process so I can actually reduce the size of the data that I need to send, or just send an effective communication part, like send the information directly instead of sending the raw data, then I would need to kind of do, for example, an AI deploy an AI model. And inference can be expensive, especially on resource-constrained devices. So one way we're looking at it is that we can distribute the inference on multiple devices and split the cost. Yep.
Quick question to you. In terms of resource constraints you are talking about, like the hardware part of it, the devices, are you considering the memory consideration or the power a challenge for edge computing?
So yes, part of the incentives on the user flavor type is that we want to basically compensate the user for the power that they're losing, the durability of the phone. This is on the user flavor. On the enterprise tactical and that type of edge, we kind of need to make sure that they're capable of doing their function. So we have developed some optimization techniques and allocation techniques to make sure that we do that without actually harming their main function.
Quick follow-up, and we're running out of time, so maybe it's for you to think, and we can discuss over the reception. But I find a big problem with your solution, because basically you're talking about distributed computing, one way of looking at it. And the trouble with distributed computing, as well as any form of highly parallel computing, is that you need to have jobs to load all those CPUs. So if you have a single thread, big job, it doesn't parallelize. So you have to have a scenario where you have multiple jobs simultaneously that you can distribute. So you have to do some kind of statistical multiplexing of jobs, requests, to the map into your CPU availability. Where do you find that the unique conditions? To be discussed later.
Well, yes, it needs to be discussed, yes.
One quick question. Could you introduce how to implement for base station or terminal for edge computing? It will be implemented on the base station or the terminal for edge computing.
So just to make sure I understand, you're asking how to deploy it on a base, like on the
right.
network?
Right.
That's a very good question. I don't have an answer ready for
thank you.
this. Oh, yeah, absolutely.
We'll need to save those questions for the reception. We're going to have a reception afterwards where conversations can further the questions and the answer period, and you as well can get involved in those conversations. So we would like to thank our speaker. Great job. Thank you, Sharif. And our next speaker to share their research with us is Amir Farouzan. Welcome, Amir.
Thank you, Sin. Hello, everyone. My name is Amir Farouzan, and I am a professor of telecommunications, someone who has spent years working on wireless, optical, and wireless systems. But today, I want to take you far beyond antennas and fiber optics to cosmic particles, the same ones raining down on us every second, and how they might revolutionize the way we communicate. Let me ask you this. What if the next big leap in communication isn't about faster Wi-Fi or new satellites, but about particles that can fly straight through mountains, oceans, or concrete walls, almost as if distance and obstacles didn't exist? Sounds like science fiction. It's not. It's called muon communication, and it's an idea whose time may finally have come. Let's face it. Today's technologies have limits. Radio waves can't travel far underwater. Optical signals get scattered by dust or rain. And in disasters or underground environments, signals just stop. We have built amazing systems, but they all hit the same physical wall. To go further, we need to look beyond traditional engineering. We need to look back into physics. 3 years ago, I spent 6 months at the Curtin Institute for Radio Astronomy in Perth, Western Australia, working on cosmic ray detection. And that's when I met the hero of this story, the muon. Muons are subatomic particles created when cosmic rays strike our atmosphere. Every second, billions of them pass harmlessly through us and through solid rock without slowing down. Having this property, they are used in muon tomography, and interestingly, one of the first uses of muon tomography was the discovery of hidden chambers in the Great Pyramid of Giza. That's when I thought, if muons can go through mountains, why not send data with them? This isn't an entirely new idea. Muon-based communication was explored decades ago, but back then, generating muons was too costly, too bulky, and too slow. Muon-based communication isn't new, it's forgotten. Like the lost knowledge of the Library of Alexandria, it's time to resurrect it. So the idea was abandoned, not disproven, just forgotten. But now things have changed. We have laser-induced muon generators, compact, controllable, and fast. For the first time, we can imagine encoding information onto muon beams to reach places no signal has ever reached before. Imagine communicating deep underwater through mountain ranges or even to subterranean structures without cables, without repeaters, without satellites. It could transform mining, disaster response, subsea robotics, and more. It's a bold idea, part physics, part engineering, but that's where innovation always begins, in the spaces we have ignored for too long. So as we stand here today, surrounded by invisible cosmic rain, maybe it's time to rediscover that forgotten frontier and turn those particles from the sky into the next great channel of communication. As I wrap up, I'd like to leave you with a call to action. This idea, using muons as a new medium for communication, is still at the frontier, but it's not just a thought experiment. It's an opportunity to build something truly new, and I'm looking for collaborators who can help make this happen. We need expertise from several directions: particle physics and detector design to understand and optimize how muons can be generated and detected, laser plasma interactions to push forward the development of laser-induced muon sources, high-speed digital signal processing to handle and decode the unique signatures carried by these particles, and communication theory and modulation to design how information can be efficiently embedded into muon streams. If this vision resonates with you, whether you are from academia, industry, or a research agency, I'd love to explore how we can work together to turn this concept into a real technology. It's a challenging journey, but also an exciting one, and it starts with collaboration. Thank you.
Great job. Thank you very much. Do you have questions for Amir?
Yes, I have one question. I'm not sure I understand what's your point. So this is the optical technology or wireless technology. It can be used for the traditional frequency or not?
I don't.
I mean, so this technology can be used for the traditional frequency band or not, or just for use optical band?
The information is modulated into particles. You don't use any of the current radio bands. It doesn't use radio bands. So it's like balls. You throw balls, and the information is modulated into these balls, which are subatomic particles, and their speed is almost the speed of light. Even underwater, they travel at the speed of light, not divided by 1.3, which is the actual light travels underwater. So we directly modulate them into particles. And there is no radio band, so you can use whatever you have.
One question, a quick question. Do you have the prototype or not?
But as I said, no, I don't have this equipment with me. Like there is, like in 1976, they made a prototype in Argonne lab in the United States, but they used proton accelerators to generate muons. They accelerate protons actually, and they hit a metal object like lead, and then muons were generated. But nowadays we have laser-induced muon generators, which are actually they have applications in muon tomography, which is used in many industries like finding heavy metals in containers and similar like that. So there's other applications, but they have forgotten that it once proposed for communication as well.
So quick comment, very interesting talk, and we really need this lateral thinking, completely new ideas. So a radio receiver operating on muons or a communications receiver operating on muons sounds very exciting PhD thesis material. My curiosity, I'm not a particle physicist by a long shot, I'm not even a physicist, let alone particle one, is if the muons go through everything with ease, wouldn't they just go through your receiver with ease? So maybe it's very hard to detect them. And we do know things like photon counting, Geiger counters. So there is a existent proof of particle counting with a long history. But I don't know if whether you can do muon counting with the same ease as we do photon counting.
Sorry, I'm not getting most of your time. It's getting
too fast. No, there is a lot of reverberation. Okay, in a few words, doesn't the muon go through the receiver, making detection very difficult?
No, the detectors are already there. When I was in Australia, this cosmic rays is a very hot topic in particle physics, because the cosmic rays are particles that have very huge energies, and so they had these antennas, radio frequency antennas, which are very expensive, like an hour, $1 million to use the telescope. But cosmic rays, very high energy cosmic rays, which are people interested in, like last for 8 seconds, like a few microseconds in an hour. Every hour you get one of those very interesting cosmic rays. And the idea was to generate these muons, which are generated when cosmic rays hit the atmosphere. And they already had these detectors. These detectors from 1976 were the first that are there. And actually, there are some physical properties of matter when something travels close to the speed of light, or actually faster than the speed of light in that matter, it generates light. It generates light, and then this light can be detected very, very well. So there's no problem at detection, but at generation, particularly very high energy, that's the problem to use this technology. Yeah.
Yeah, I have one comment and one question. So you summarized well the property of this particle, but you didn't. It would be nice if you have a couple of slides to summarize what is the main technical challenge of communication, then what is your plan to address this? Then, yeah, that would be nice. So because I know it's 5 minutes talk, but
well, I have done some maths and simulations about this technology. The distance a particle could travel when the speed is close to the speed of light is proportional to its energy. It's better than classical mechanics. Classical mechanics, you have this, because muons have a lifetime, and in their time frame, they will disappear soon, but because they are traveling at the speed of light, it's a time dilation, if you know, like time slows down for muons. And after doing the math, we find out that they can actually do better than if they were their physics governing them was in classical physics, because you have this E equals 1/2 m v to the power of 2 for Newton law. But for there, it's like the distance traveled in that lifetime is proportional to the energy. So the higher energy we give to these muons, we could send them farther distances. So for now, with the generators, I know that it could work very well in dusty rain areas. You know, already there are some companies working on FSO, free space optical communication. And that the problem with that is that with a slight dust or rain, the link will disappear. But for muons with current generators, we can have a very good communication. But if like this building, you can communicate with current. I guess I'm not sure, but you know, it's something that should be experimented. You can't do the math and say, okay, we are good. So it needs some support to have this prototype built and experimented. Actually, I can't say for sure what will happen, but if we manage to do this, then
all right, thank you.
Conversation we need to have at the reception. It's a much longer conversation, but thank you very much for your questions. Thank you for your presentation. And our next speaker is Ahmed Naguib. Okay. There you go.
Okay. Hello, everyone. My name is Ahmed Naguib. I'm a postdoctoral fellow at Queen's University in Canada. I completed my PhD at the School of Computing at Queen's as well. Today, I'll be talking about safe and explainable AI-driven control of next-generation networks. I think everyone here knows about this instance. A few weeks ago, AWS experienced a very significant outage that actually affected many services around the world. And Amazon later announced that the main reason behind that was an automation bug. And mainly this affected like gaming platforms, web applications, and even smart devices. Although this example is not really AI-driven automation bug, but at least it's an example that gives us an idea how automation can be disastrous. And this becomes more critical when we talk about AI-driven automation in next-generation wireless networks, especially with the global push towards AI-driven telecommunications, which is demonstrated in collaborations and funding of many mobile network operators and telecommunication vendors, and even AI infrastructure developers. The main issue here is when you have an intelligent agent that is trained in like a system level simulator offline, and then you go and deploy it in a real network environment, and it suddenly sees a condition that it never experienced it before when trained offline, it will end up taking risky decisions, which will end up, as you can see in the figures here, in like violations of service level agreements, cascading failures across the whole network, which also comes hand in hand with the dimension of unexplainability, where like you end up using black box models, even if you use reinforcement learning agents that does not require the use of labeled data sets, but it still do not come with explainability by default, because we are using neural network deep architectures. And that's why we are mainly proposing TrustRic, which is a framework or a blueprint for safe and explainable AI control of next generation networks. And the main component here is like a safety gate, which tries to only accept actions that fulfill the service level agreement constraints and some minimum confidence and clarity threshold, Otherwise, we will have to use traditional solutions as fallback policies. I know that the safety, this is like a simplification of the idea. There are lots of explorations to be done at the safety gate. We have already explored some ideas on smaller scale, but we're interested in extending that on larger scales in more realistic scenarios. And that's why we're trying to build trustworthy AI for network control. And this is not just a one-step process, it's an iterative process that requires collaboration. And that's why we at the Telecommunication Research Lab at Queen's University in Canada and Waves Lab at the University of Calgary, also in Canada, are seeking industry partnership, mainly to collaborate on prototyping and deploying trustworthy AI for network control, which requires access to equipment and system-level simulators that will give us access to realistic network scenarios to try also fund personnel such as master's and PhD students and undergraduate interns for testing and validating our proposed ideas. We have previous experiences with industry partners such as Ericsson Canada, where we had like an insert strategic project on AI-driven resource management for next generation mobile networks, which mainly was worth like around 590,000 Canadian dollars. So yeah, that's it for my talk. I listed all my contact information here. And if you're interested in more information about my proposal, you can visit the website linked to my QR code. Thank you very much for listening. And I will be happy to take your questions.
Okay, great. Thank you. Okay, who has the first question? Pavel.
So what kind of collaboration are you looking for in terms of hardware and infrastructure from companies?
What kind of hardware do we require? So for instance, NVIDIA has like very small base stations that support L1 and L2 programmability right away. This would be a very interesting device that we'd use as a base station to try our proposed algorithms related to generalization, explainability, or generally trustworthiness in realistic scenarios.
Thanks.
So maybe a little offside because it's not my field, but seems that like 100 chimera. So we know that large language models inherently create sequence of language out of the training data set by essentially cut and paste. So when you start going down in the probabilities and I don't know, it picks up at random anything and it hallucinates. Now here you're promising us to ensure its accuracy and reliability. Well, everybody would want that, but nobody's being able to deliver. So I'm a little skeptic that you actually have a solution. The problem is well formulated, but what exactly is the breakthrough that would enable you to have a trustworthy, reliable, machine learning or large language models? What I read is that if you put guardrails to ensure that, the actual output becomes uninteresting.
That's a really good question. It's not like a one answer question, but like, for instance, I can show you from my backup slides. We're looking to have a standardized architecture, such as an open radio access network that explicitly address some dimensions related to trustworthiness, mainly generalization, safety, robustness, and explainability. All the work out there in literature is just using, for instance, reinforcement learning without giving any consideration to any of these dimensions explicitly. So having these directly reflected in the standards would be one step towards that. There are lots of approaches to explore. For instance, we have already explored some approaches on the safety and generalization dimensions, and we proved some successes on small scale scenarios, but that's why we're looking for collaboration with industry partners to see if these algorithms would work on realistic scenarios, large scale scenarios, and so on. So approaches are there. We have like a list of approaches to try, But the thing is, for instance, here we have generalization strategies as well. But the thing is, if you look at this slide here, the main problem is we don't have our own challenges. One big problem in the wireless domain is we don't have our own challenges. We always, for instance, in reinforcement learning, we just reproduce what's being done in robotics or gaming fields, which is a big problem for wireless domain. In wireless domain, we have to have our own defined challenges so that people would just use, for instance, as a system level simulator that behaves exactly like what's expected in the network. And we have a very well-defined problem that people are competing to solve the problem using this standardized system level simulation. If we don't have that, we would not even know whether the like spectrum of approaches I showed you would work or not. So one big problem is like having benchmark challenges defined by the wireless community itself. And of course, it requires industrial collaboration. Also, a very promising approach is like having foundation models for wireless networks as well, not large models, foundation models for to be used as like very like a good way to jumpstart learning instead of learning from scratch for a group of tasks. For instance, resource allocation tasks. It doesn't have to be large models at all. It can be a small wireless networks model that is sophisticated for resource allocation or resource management related tasks, for instance.
If time's still enough. So I see that you're already working with Ericsson on this, right? There's a slide mentioning the collaboration. Yeah.
Yes.
Too bad Ericsson is not here today, but yeah, I think so. In parallel, in finding some hardware platform to test your algorithm, you could actually propose it to the ORAN Alliance in parallel, because for it to be standardized, it's not essential to test it on a hardware platform. You could just convince people if you can. So that could be something that you can do.
Yeah, thank you very much for the recommendation.
Last short questions.
Yeah, thank you for the nice presentation. I think you'll probably face two challenges. One is how do you get the reliable data that's truly representative of the network behavior? The challenge would be if you run into problem, you have to fall back, which means you have to implement the fallback algorithm plus the AI algorithm. So in that sense, you may have some cost issues because you have to do both.
So to answer the first question about like collecting or using representative data, there are like lots of approaches to at least explore. So for instance, domain generalization approaches, like how to simulate the data, how to combine between synthetic and realistic data and so on. But these are just, you know, one dimension of the problem. Like generalization is just one dimension of the problem. And there are like some ways like domain generalization and synthetic data collection that needs to be explored and checked if these approaches would really, like building models based on these approaches would really solve the problem in the realistic deployment environments. That's one part of your question. The second part was about, sorry, what was the second part about?
You have to do the AI model plus the fallback model. So you have to implement both systems in a sense.
Yes, so the thing about mentioning the fallback solutions is like people just, when like proposing AI solutions, they just neglect the traditional solution without paying any attention to it as if it doesn't exist, and they don't even compare against it. So knowing that a certain traditional solution would be, for instance, excessive in resource usage, but still would not be disastrous as a random action taken by a reinforcement learning agent, would still be good enough to have some estimate of how this traditional solution would feel like or behave like, because it's well known, been used in the system and so on. So my proposal is like deny by default, like we do not accept any random actions by a reinforcement learning, for instance, unless it's we have like some certain confidence level defined as a cost function reflecting explainability and safety to make sure that it is reliable enough, which is not an easy task, I understand, but we have like several ideas in mind. Thank you.
Right, great. Thank you so much. Our next speaker, Aditya Pawar.
Thank you, Sin. So what is the most dangerous threat to our autonomous future? Is it a sophisticated cyber attack, a software bug? No, it's a few $100 device that fits right in the palm of our hands, a simple jammer. With one flick of a switch, a convoy of self-driving trucks on the highway doesn't just stop, it leads to a multi-kilometer catastrophe. This isn't science fiction. In 2023 alone, there were hundreds of reported incidents of GPS jamming that led to disruptions in aviation, shipment, and logistics. Now imagine that scale to 6G. That is the brutal world that we are building towards, unless we change the way we think about security. My name is Aditya Pawar, and I'm a researcher at CP Technological University in India. Working in financially constrained environments has taught me how to create precise and cost-effective solutions. My background bridges RF engineering and cybersecurity, and my research in AI-driven anomaly detection and digital twin modeling focuses on how wireless systems behave in real-world stress. We're all here because we believe in the power of 6G, a seamless world with instant and reliable connectivity, powering everything from industrial automation to truly smart cities. It's a future built on the foundation of flawless communication, with global 6G investments projected to reach around $100 billion by 2030. The stakes couldn't get any higher. We, as researchers and industry leaders, are building the nervous system of the 21st century. But this nervous system lacks an immune system. That simple jammer I mentioned before acts like a virus that can paralyze the entire network. And how do we deal with this today? With brute force. We deploy massive antenna arrays that are too large and not scalable with the edge devices that 6G will depend on. We're trying to protect a living and breathing network using an old and rigid armor. This is broken. We need edge-native security that scales with the network, not against it. So we decided to build the immune system. We've created a smart, lightweight, and cost-effective security platform to hunt and neutralize these jammers. Our solution works like a swarm of digital bloodhounds. It creates a radio map of the environment continuously, and when a jammer is turned on in the environment, it creates an anomaly, a scent which our bloodhounds detect and pinpoint. Using an elegant hybrid of geometric modeling and triangulation, we're able to locate the jammer in real time and in 3 dimensions. Crucially, our system is protocol agnostic and can be seamlessly integrated with the current 5G and 6G networks without overhauling any of the current infrastructure. But our expertise doesn't just stop there. Our research delves deeper into creating sophisticated surgical jammers that target niche vulnerabilities such as the guard bands in OFDM subcarriers. This unique poacher and gamekeeper approach allows us an unparalleled advantage. We know how to build the lock because we also know how to build the key. Because of this, we are able to transform the economics of network security. For telecom operators, it means gaining a resilient and self-healing network with edge-native threat detection. For defense agencies, it means gain spectrum dominance with lightweight and deployable tools for threat neutralization. And for smart cities, it means gaining scalable protection for thousands of IoT endpoints. We have a clear roadmap to evolve this platform into an AI-driven system readily deployable at scale. With industry support of around $200,000 through financial, hardware, and intellectual resources, we're confident that we can transform this platform into a full-fledged field-ready solution. Our goal here is simple: to earn the next meeting, to search for partners that see what we see and who are willing to help us take the next step. We've come this far by turning constraints into creativity and challenges into breakthroughs. Now with the right partners besides us, we can take the next leap. So let's build a 6G that's not just powerful, but unbreakable. Yeah. Yeah.
Okay, so I'll be a little direct and absolutely did not get at all the idea other than a wishful statement. So yes, we want a 6G that is unbreakable.
Yeah.
What are you going to do about it other than a bunch of drones? I mean, plenty of drones, people play with drones, 20,000 drones in China. It's, today commonplace. How does it fix the situation where the driver has a heart attack and you get a pileup of 10 cars on the highway? You need tow trucks to come and remove the obstacles. What is your solution going to do?
So what we do is we are continuously, so we use agents. So an example is digital bloodhounds who continuously they are continuously monitoring the environment and creating radio maps. So we are backtracking where the jammers are. And once a jammer is turned on, there is this differences in the signal levels and such things we parameterize. And then based on that, we're able to detect that a jammer is there. But our main focus will not be on to detect jammers because anyone can do that. That's traditional. But we want to localize those jammers. Localizing a jammer requires an antenna array, which depends on angle of arrival and then triangulation. But we want to go beyond that because in 6G, you cannot be deploying.
Forgive me, if 5G, even if not 6G, with integrated communication and sensing can very easily detect that there is a pileup and 3 cars hit each other. That's not going to be the problem. The problem is, do we have any better solution than wait for the tow trucks to remove the obstacles? And I don't know that software agents in any imaginary AI-driven software solution is going to deal with the physical environment.
I'm sorry, I couldn't get it.
So the problems in a traffic accident is physical.
Yeah.
They cannot be dealt with software.
So we're not trying to solve the crash part of it. We're just detecting. So if when a crash occurs, because let us say there are a few trucks on the highway, and when the signal is jammed, that time because the signal is jammed, there's no communication between the trucks. So that's why the crash occurs. But if we have already detected what jammer is there and where it is localized, so if you can neutralize that threat, then there will be no crash. So
well, I mean, some crashes are unpredictable. Like I imagine I picked the right one. Driver has heart attack.
Yeah.
And collides happens within seconds, right? Now, and detecting that is not a problem. 5G, 6G is going to do that. So I don't know exactly what is your value proposition.
We are working on jammers specifically. So where a human-induced error occurs, so that part we are not trying to solve exactly from our research.
So can you summarize what's your present, the key technology is what? Keywords, what's the key technology?
I can't hear because of the reverberation.
I mean, what's the key technology, what you present just now? Can you summarize with one or several words?
Can I summarize?
Yes.
Yeah. So it's
short.
Yeah, sure. Yeah. So essentially what we create radio maps, and through that we're continuously trying to detect where the jammer is, but detection of, as I mentioned before, detection of jammer is not what we are focusing more on. We're focusing more on localizing them because localization is the bigger threat. Even if someone knows a jammer is there, it's not easy to localize them, and which is why we're working on creating this a bit more complex hybrid that can help us easily localize these jammers.
Yeah, maybe just a general comment. Since you have only 5 minutes, to convey a complex idea or technical details, it's much better if you prepare maybe a few more slides than just one, right?
Yeah, I'm sorry.
You have like 2 dogs and a few drones. With that, it's very hard to convey your message.
Yeah, I understand that.
In terms of the the research or technology readiness level, where are you at now? How much work? How much work has been done already?
How much fund has already been done?
Yeah. What is the readiness level like?
So actually, I'm an undergraduate student, and this is my own venture. So I'm trying to I started off with anomaly detection and self-healing networks. Through that, I've worked my way around and then working on jammers and on detecting jammers. So currently, I have some done work on this, but there's no funding to it. So the university is not funded as much, and which is why I'm here asking for some support.
So you have a huge wall, huge height of a wall to climb over. If it's going to be massively applicable, then you need to rely on cellular networks. Cellular networks are not going to accept anything is outside of 3GPP standards protocols. So you should really immerse ourselves onto 3GPP, joint communication and sensing deployment scenarios. Some of them are precisely what you're talking about, accident detection and prevention. Yeah. And if you can get your ideas into that language and into that context and make it into some technical contribution to 3GPP, then you're golden. You may have what is called the implementation exclusive patent. Then you get the royalties for the rest of your life or for the rest of the life of 6G. So go ahead. But you have to speak the language of the relevant audience, which is 3GPP.
Yeah, so the thing is that recently, like very recently, last year itself, we were granted a 5G base station, but that's all that we have. We don't have much hardware to work with. And since we have a 5G base station, so most of the projects are related to IoT applications using 5G. And then if you want to really work on 6G and target such things, so I need some funding or something like that. Yeah.
Great, thank you very much. All right. Our final research pitcher is Angela Wadhaka.
Imagine if your internet could think ahead, even when your computers can't. Imagine living in a world where your connection doesn't drop just because your connection doesn't drop just because your town doesn't have shiny towers or supercomputers. In many parts of the world, this is not an imagination, but it is a reality. Weak signals, slow speeds, and constant disconnections. And yet, these are the same communities that rely on reliable connectivity for learning opportunity and healthcare. I'm Angela Waithaka, a fourth-year biomedical engineering student from Nairobi, Kenya, and my research asks one simple but a very powerful question. Can we make communication systems intelligent even when the resources are scarce? Modern communication systems like the 5G network, IoT devices and the cloud services, they rely heavily on machine learning and artificial intelligence to keep them fast, efficient, and reliable. But here's the problem. These AI systems, they are too heavy and they require huge data centers, massive computing power, and endless electricity. So when you move from a city like Nairobi to a rural county, or when you travel from a country like Japan to Kenya, the intelligent communication system suddenly becomes not so smart. And the result, a digital divide that keeps entire regions offline and millions of brilliant minds disconnected from the global economy. My research proposes a different approach, one that is built for real-world constraints. I aim to develop lightweight adaptive AI models that don't require giant servers or constant high-speed internet connections. Think of it like teaching your network to predict the weather, but instead of rain, it predicts congestion, poor signals, and data loss. It will learn to adapt automatically by allocating resources smartly, reducing energy use, and keeping communications flowing smoothly, even when the conditions are tough. And instead of sending everything to the distant cloud servers, I'll be using edge intelligence, which are faster, cheaper, and they can work even with reduced bandwidth. This means that the data will be processed right where it's created. But what makes my approach different is that I'm not just putting AI at the edge, but I'll be combining edge intelligence with smart optimization methods. This means that the AIs running at the edge will be able to adapt, learn, and make predictions even when the resources are low, like low power connectivity and data. So by training these lightweight AI models to make intelligent decisions locally will be able to make the people in the rural or resource-limited regions have access to reliable connectivity, even when the cloud access is unreliable. So in other words, I'm bringing the power of AI to the people who need it the most, because smart connectivity should not just be for smart cities or high-tech hubs. It should be able to thrive anywhere, even when there is low infrastructure. This impact goes far beyond technology, because this work can really help students from rural schools be able to join online classes without frustrations, empower local businesses to access cloud services so that they can be able to compete globally, and it can be able to help remote hospitals get access to digital health systems. In short, we'll be bridging the gap between innovation and inclusion, because the future of communication should not depend on where you were born or how powerful your hardware is, but it should depend on how intelligently we can make use of what we already have. Through this research, I'm looking to collaborate with telecom companies, IoT developers, and cloud service providers to test, refine, and deploy these adaptive AI models. One of the key application areas I'm exploring is a digital health twin projects, which are intelligent virtual replicas of a patient that use real-time data to support personalized treatment plans and predictive healthcare. This means that a local clinic will be able to get patient data instantly, securely, and the doctors can make data-driven decisions, even in the areas we have unreliable connectivity. So my goal is to ensure that the people in these rural areas and the resource-constrained environments be able to enjoy the benefits of advancing technologies, as those in smart cities, because it's all about connecting the unconnected and transforming access to digital healthcare across Africa and beyond. So together, we can transform connectivity in regions that have long been left behind, proving that smart, predictive communication can reach everyone and everywhere. Because I believe when every community can connect and every mind can create, that is when innovation becomes truly global. Thank you.
Questions for Angela?
Yeah, very good presentation. I commend you for your deeper commitment clearly expressed on the societal values and equity, access to broadband, et cetera, and preoccupation for digital gap, connectivity gap. That's all fantastic. The summary, I believe, is that you are going to try and move in that direction through real-time adaptability to network changing conditions, propagation, interference, et cetera. Through AI/ML. Exactly how, you didn't say. However, I have to alert you that the tremendous success of cellular networks is because over 5 decades, engineers have been addressing precisely those problems. So the current network, through pilot probing of the channel, real-time channel estimation, real-time adaptability in modulation coding schemes, MCS, is creating a very tight choice of physical layer parameters to the propagation conditions, including interference. And on top of that, as you move around, is keeping listening to these probing pilots from other base stations, is keeping a list of targets. So as you get towards the edge of the coverage zone, the base station may decide that it's better to hand you over to the next base station through handoffs. So through the use of, in summary, adaptability in the physical layer, adaptability in the handoff, and adaptability at the resource allocation and scheduling, the networks are incredibly resilient and adaptable. You need to do your homework and show with numbers in what way you can do better. Because the engineering community would be highly skeptic as to you can improve on the state of the art.
Sorry, come again. I'm still not getting.
So you're proposing great things coming from adapting to time varying conditions. Well, the current systems do that already. So now you have to prove that you can do better. And that's a high bar to jump.
Should I give you, let me give you like a short summary. So in what ways my research will do better for the communication systems that we have right now? Well, I come from Kenya, and I can tell you that the advancing technologies that other countries experience, it's not the same in Kenya. In Kenya, you'll have cities, major cities are the ones that enjoy reliable connectivity. So you go to a rural area like Turkana is a county in Kenya, and they don't enjoy the same benefits. So for me, what my proposal, what my research will do is make those people, the people and the communities in the counties that have not yet received these advancing technologies that we talk about, be able to access them.
Believe me, my heart is with you, and I understand what you're saying.
Yes.
But I think to be successful as an entrepreneur, you have to be able to separate the emotional and societal commitment from the solution you're proposing. So many parts of the world, not just Kenya, many parts of the world, even advanced affluent economies, as you go into rural areas, there is a point where its business case doesn't pay anymore to provide coverage. And beyond that point, whoever is living there is probably very low density, doesn't have coverage. It's an economic problem, not a technical problem. So you can, the cellular companies could provide coverage to these people out in the suburbia, rich or poor country, but somebody would have to subsidize it because in market economies, the money is not there. So it is a socioeconomic problem, not a technical problem. So if we stick only to the technical problem, then it collapses to, can you do better than the existing solutions? And that's a high challenge to overcome.
Thank you for that.
Yeah, thank you very much for the very nice presentation. I think I should congratulate you for the first of all, you address a very important problem for your country. Secondly, you list out the problem and your solutions clearly and present it very clearly. That's you did a good job.
Thank you.
I have two comments. One is, indeed, the problem is hard because we need to build cheap, reliable network for the countries that doesn't have enough resource. I think what you chose is like a theoretical way or research way of using AI to solve some problem. That's good for research direction, but at the same time, we can also look at the practical solutions to see what are the deployment choices to solve some of the problem. Not everything, because if it's underdeveloped country or area, using AI is going to be even harder. Using simplified existing solutions may be a shortcut. So if you want to do near-term solution, maybe just look at network optimization, look at what are the lower end or device, what are the simplified solutions you can deploy to help build up the system. But on the other hand, you can always choose AI-based research direction to see what are the solutions you can additionally do. But in general sense, using AI may or may not reduce the cost and make it easier, right? If the current infrastructure doesn't exist, maybe building an AI system is even harder, right? That's my comment.
For that, actually, we thought about it, and we will start with affordable, like for the IoT part, we'll start with affordable IoT sensors because they're usually low cost. And then when we develop a prototype that can work for IoT, that can work well with IoT, then maybe we can move on to collaborate with telecom companies. But I get what you're saying. Yes, when the infrastructure is not there, it makes it really difficult to use AI. So we'll start with IoT devices, the sensors, and if they are able to provide the data, then maybe now we can bring in the telecom companies in the country that can help us now bring AI into those devices that are used in those rural areas to make maybe yes, to make somehow it a reality. Yeah. Okay.
Yeah, thanks, Angela, for the very good presentation. So I also agree that connecting the unconnected is pretty important, and it's actually one of the goals for IMT 2030 as defined by the ITU. And also our team here at ZTE also contribute a lot to the network deployment in Africa and also in this area, the Middle East. So I think if you're interested, we could have more discussions off the stage to see whether we could bring some concepts, for example, particularly to the ITU, and try to make some impact to the IMT 2030, the overall framework or the performance requirement or the evaluation, those technical documents to try to reflect some of the points that you make here. Yeah, thank you.
Thank you so much. I'll definitely take you up on that. Thank you.
Great job. Okay, I would like to ask all our research pitchers to come up on stage. And I just want to take this opportunity. Let's make sure we get them all up. Where's Angela? There she is. I would like to take this opportunity to applaud these brave young people who brought their problems to our Innovation Scouts. Great job, all of you. And I especially want to thank our Innovation Scouts. I appreciate your questions, and I appreciate your willingness to continue conversations with these folks. And we will be asking all of you to be willing to chat with our Innovation Scouts and our research pitchers at our reception. And we will be broadcasting much of this research pitch. So there may be people who are going to be watching this who will also like to follow up with conversations. So thank you all. We will chat more at the reception.